Good morning, everybody. It's a distinct pleasure to be speaking to you all right now, albeit in this online digital way. My name is Francesco Bullo. I am a faculty at UC Santa Barbara, and today I'd like to talk to you about network systems, Kuramoto oscillators, and synchronous power. First off, I'd like to start by thanking the kind organizers, including General Chair and Co-Chair and Program Co-Chairs, Professors Kim, An, and Shin. Thank you so much for having me here. And second off, I would like to express how terribly sorry I am to be unable to be there in person, enjoying your company. And I very much sincerely do hope that we will all be able to travel again and visit, and for example, I'd love to visit Korea. So, having said that, the work that I present today is the achievement of my postdoc, Dr. Sabir Jafarpour, and one of the works is in collaborations with two younger scientists, Elizabeth Wang and Kevin Smith. So let me give you a very brief introduction into this broad set of problems, which has to do with the study of multi-agent complex systems, which I will refer to as network systems in the course of this talk. And so we are interested in studying high dimensional systems, dynamical systems, and their interaction. So that's the basic idea. And one of the main paradigms in this line of research is to understand that these network systems are designed and evolve because of a function that they perform. So there's a function that we are interested in. It's not just a control problem where I wish to stabilize an equilibrium, regulate the behavior. I'm really interested in understanding what that behavior may be and how to translate that into a dynamical and control system analysis. So, and this function, as illustrated by that picture, is determined by the structure of the network. So we are interested in this nexus here between the two. And this nexus is very well understood for simple linear systems. So here, for example, allow me to show you two quickly simple examples. Classical examples arising from sociology and from ecology. People have studied averaging systems. This is a continuous time linear system, and it's been understood that these systems are described by a so-called Laplacian matrix. And averaging systems are known to have a certain desirable function, which is that of achieving consensus, so all nodes in the system will reach the same value. And it is well known that consensus is reached if and only if the underlying network has a certain structure, has a certain graph theoretical structure. Here, without going into the detail, that structure is the existence of a globally reachable node. The other basic continuous time linear network system example that I wish to mention is a classic desert ecosystem model by Neumayer 73. I'll refer it simply as a network flow system. It's also described by Laplacian together with some outflows. It has an input. The matrix is more generally referred to as a compartmental matrix. Nevertheless, in flow system, a stationary distribution is achieved if and only if the underlying topology of the graph has the property of being outflow connected, which means from every node there is a directed path to an outflow. So now these are two classic examples where structure and function are fully understood, and these are two examples that are linear. Now, the complete theory of linear system, here this is an advertisement for a book that I published. This is a textbook for first-year graduate students. It is freely available on my website, together with slides and together with solution manual for instructors. And this is a beautiful theory that has been developed over decades of work, and it's relatively comprehensive and exciting to be immersed in. And so, with that as a background, of course, the state of the art and the key challenges in today's world have to do well, in this context of scientific endeavor, has to do with studying more complex systems, such as studying, for example, the limit as n goes to infinity for the linear case, or studying the presence of maybe stochastic effects, or finally, what I'll talk about is studying the case of nonlinearities. And there are a broad range of nonlinear network systems. There's a catalog of such examples that I could describe. But in order to be concrete and show you detailed results, I'm going to focus on one nonlinear network system that is of great importance and interest in my opinion, and that is the case of Kuramoto coupled oscillators. And I will today talk about both. I'll talk about their synchronization, meaning to say their synchronous behavior, the synchronization phenomena, the existence of this behavior, and then later on in the talk, I'll talk about multi-stability in the Kuramoto coupled oscillator model, which means, you know, existence of multiple possible stable solutions. And I have live links here for when you will download the slide if you are so interested. So let me get started and talk to you about this model of coupled oscillators. So each oscillator, let me for a second draw, hide away this part of the equation. Each oscillation, when decoupled from the network, obeys a very simple first order equation. So it's really just rotating with a natural frequency. Each oscillator is described by an angle and by a natural frequency, an angle theta I, a natural frequency omega I. Now, the matters become interesting when you couple them. So coupling here is described by a collection of coefficients of strengths, Aij, and the modality of the coupling is that the coupling is modulated by the sinusoidal function of the phase difference, right? So this is the equation for node I, and you see that angles theta j's at other nodes j are appearing in the equation. So now I have a couple network of oscillators. This is, in a certain sense, this is a prototypical model for coupled oscillators that appears naturally in a broad range of applications. Now, this is the model I have talked about. I am interested in a simplification and in a generalization of this model. It is rather simple to ask yourself the question, what if I assume that angular velocities are zero? Can I find equilibrium solutions? And so that is the Kuramoto equilibrium equation, which I'll talk about more in detail in what follows. Those are equilibrium. It's also possible to take the Kuramoto oscillator and set oneself in a rotating frame. And in a rotating frame, what appear to be rotations at constant angular velocity become now equilibrium points. Now, it's also possible as to generalize it. And it is clear that the Kuramoto oscillator is obtained in the viscous limits when damping is large and masses are small for the so-called coupled swing equations. These are Euler-Lagrange equations that can be understood in two ways. One way is their classic equation describing the evolution of power networks and in the transmission regime. And alternatively, in a very simple pictorial way, these equations of motion are describing the exact mechanics of this spring network on a ring that I am illustrating on the left, whereby beads are rotating and they're interconnected by ideal elastic spring. And a little bit of calculation show that the presence of the spring leads to this sinusoidal nonlinearity. So now, what is another way in which the equilibrium equation appear? The Kuramoto equilibrium equation are identical to the so-called active power flow equation. What are the active power flow equations? Well, it's the idea is that you have a power network, an energy system. At this moment, I'm going to assume no storage and no dissipation. Some power is injected at a node, and after it is injected, it must flow to neighboring nodes. Perhaps it's extracted. So when I say injected, it's going to be algebraic, right? Positive or negative. And so that's the first equation. That's kind of like a Kirchhoff balance equation. It would be the Kirchhoff current law. But here I'm thinking about power instead. Later on, we'll have a Kirchhoff voltage law. And then, of course, how much power flows on any given edge? How much? Well, that is well known by power engineers that the amount of power on a given edge is determined by the power angle on that edge. In other words, if I have an angle, if this is node I and that is node J, I look at the angular difference, theta I minus theta J. I call that the power angle for the line, and the max and the amount of power depends upon the sign of that angular difference. And there is a maximum value, Aij. So Aij in the previous example was the strength of the springs. In this example, it is the maximum amount of power that can be transmitted on a given line in an alternating current circuit, of course. So this is the alternating current mode, lossless. Now, so I have now illustrating two equations, one and two. When you plug the second into the first, you obtain exactly the Kuramoto equilibrium equation I have shown to you here. And so, in the context of power systems, there are several questions that naturally arise. I give you this coefficient Aij, which I refer to as spring stiffnesses or admittances in an electric circuit. I give you the supply-demand vector, the injections of power at the various nodes. And so given the network parameters, the topology, as well as the load and generation profile, which is vector P, relevant questions of interest include the following four. Does there exist a solution to the equation? That means an operating condition. Is it stable, by the way, in some sense, which I'm not going to do. What is the network capacity? Meaning to say how much power can be transmitted? How large can these entries P be? By the way, is there a solution? We will see very soon that a condition is that the sum of PI must be zero. So there must be balanced injection and a balanced power injection, a balanced supply demand vector. But that's not going to be sufficient if necessary. How much power can I transmit? Another one is, how far am I from loss of feasibility from the network being unable to transmit that power? Because that for sure will mean that that I am close to some instability, to some bifurcation, and something typically practically undesirable will occur. And finally, this is something for the second half of the course, is my operating condition unique or are there others? And we will see that there are several for this set of equations. So, okay, so these are interesting questions. And from a dynamical system phenomenological point of view, if you just take these ordinary differential equations and you simulate them, depending upon the values of the parameters, you see that in some cases, for example, here one node oscillates clockwise and the other two oscillate counterclockwise. So here at the case of n equal to 3. Or in some other cases, yes, they do. There is a transient, they do oscillate, they don't come together. They never come together, perhaps, but they are converging to having the same angular frequency and a steady angular difference, right? And so we want to understand, when do we transition? When are we in the regime of, uncohesive behavior, and when we are in the regime of synchronization? This is a synchronization regime. This is frequency synchronization, because the phases continue to be different, but the frequencies become identical. There is another phenomenon, which is that of multi-stability, the existence of multiple solutions. I'll talk about that later. So let me do a little bit of modeling so that I can tell you about the state of the art, our progress, and some numerical results illustrating how our progress, how far we are along in understanding these active power flow equations, which are the same as the equilibrium Kuramoto equations, and therefore the existence of synchronous evolution for the Kuramoto model. So I need to introduce three matrices, B, script A, and L. This is called the incidence matrix, describing which node is connected to which other node. This matrix has the feature that when I apply B transpose to a vector of supply demand injections, then, and that's a vector of dimension m as the number of edges. I'm in a graph with m edges and n nodes. The outcome of B transpose P is the pairwise difference on the edge from I to J. So this operation extracts from supply demand the pairwise difference. The second matrix is a diagonal matrix that contains all of the admittances of all the lines, all the spring stiffnesses, in a diagonal matrix. So it's a diagonal a matrix with positive entries on the diagonal. And finally, it's well known from algebraic graph theory that for an undirected graph, such as the one we are discussing right now, if you combine incidence and weight matrix in this particular product, you obtain the famous Laplacian stiffness matrix, also called Kirchhoff matrix at some point in time. This matrix is positive, is known to be positive semi-definite. Now, algebraic graph theory gives us a lot of really elegant and powerful tools in order to understand this type of problem. So early on, when I said I want to relate function to structure, well, the structure will be formalized using algebraic graph theory. So let me give you a little bit of useful algebraic graph theory and leading up to the problem at hand. First of all, as I said, the Laplacian is positive semi-definite. One eigenvalue is equal to 0. The other ones are all positive, or at most positive. It could be 0 itself as well. It's well known, one concept is that of the use of the second smallest eigenvalue of Laplacian, that's lambda 2, and it's referred to as a connectivity. It has to do with the connectivity and the coupling of the graph. If you increase the admittances, lambda 2 will increase. That should be important because we have this intuition that the more connected, the more coupled is the network, the more power it should be able to carry. The other is, let's look again at our equilibrium equation of interest. Right now, I have written it in vector format. It turns out that with these definitions, I can eliminate the summation under I, and everything comes together, and I obtain that the supply-demand vector is equal to B script A sinusoidal, I need to say a vector of sinusoidal functions, applied to the pairwise angular differences. And now, if the pairwise angular differences are small, so if I assume that theta I minus theta j is relatively small, is approximately small along every edge of the graph, then it turns out that, of course, you can eliminate the sinusoidal dependency, and actually you recover L. You recover L. Why is this important? Well, let me just show you two examples. So I am sure you have all studied linear spring networks, right? For example, undergraduate example may have been a spring network in one dimension, right? Or an undergraduate example in electrical versus instead of mechanical engineering, maybe that of a resistive circuit. You inject some current, you withdraw the current, you have some resistances, and you're interested. Here on the right, you're interested in determining the voltages at the nodes of the circuit. And here on the left, you're interested in determining the positions of the mass. Now, it turns out that if you're thinking of this as static problems and you're trying to find equilibrium solutions, well, then the equations in both cases is an equation of the form, exactly of the form from a previous slide. It's an equation of the form, a Laplacian matrix multiplied a vector of variables of unknowns must equal a supply-demand term of sorts, right? On the left, you apply a load force. On the right, you inject some current. And so the problem at hand is very akin to that of finding equilibrium of such systems. And so let's discuss this problem. So this is the problem. This problem has a name. You could say this is a linear equation, or you could say this is a balance equation where the matrix is a Laplacian. So it's a Laplacian equation or a Laplacian system, referred to. And it turns out very easy that the solution exists, not unique, but solution exists if and only if the supply-demand vector is balanced, meaning to say as much current is injected as withdrawn, how much power is injected as withdrawn, as much force going to the right as is to the left. So now, should the equilibrium exist, then you would have, of course, a solution to this equation. One solution would be of the form L pseudo-inverse times the supply-demand vector, right? This is very elementary. And similarly, suppose that I was interested in understanding these pairwise displacements, right? Or the voltage drops here from one node to the other. How do I recover them? Well, these voltage drops, pairwise displacements, are B transpose theta, and theta is L pseudo. So the bottom line is that I obtain this quantity, which at first sight seems unwily and unusual, but it's actually, after some thinking, it's really very intrinsic to the problem. So B transpose L pseudo times the supply demand, that tells you the pairwise displacement, right? The relative displacement. So this would be the exact solution if we are in the setting where these pairwise angles are very small, but we are precisely not interested in the linear behavior at very small angles. We're interested in the large scale solution. So, so here is the problem, right? I'm given some supply demand, and I have the topology and the parameters as codified by the matrices B and script A. And the question is, can I find operating conditions theta that make this equation come true, right? Now, in the literature, two tests are known, two sufficient conditions are known. I use the letter T to denote the test, right? And this is all because these are in the literature. I'll show you our new results immediately next. And these results are based on either the 2 norm or the infinity norm. So we have sufficient conditions on the parameters of the problem that guarantee the existence of this synchronous behavior, the existence of this power flow. What are the sufficient conditions? Well, in the case of the 2 norm, here is what should be satisfied. You want to satisfy the fact that B transpose P active, so now this is the pairwise power injection differences. The 2 norm of that entire vector with M entries, where M is the number of edges, has to be dominated by the connectivity of the graph as measured by the lambda 2 eigenvalue. So this is the old 2 norm test, and it's strictly guaranteed to be correct for unweighted graphs. And there are conjectural workers for weighted, but they are unproven at this time. Also, there is an infinity norm test. This infinity norm test, what does it ask for? Now here, it's not the pairwise power injection differences, but rather it's precisely the pairwise displacements for the linear problem. So this test is saying, hey, take the pairwise displacement of the linear problem, and if those are upper bounded by, each one of them is upper bounded by 1, or their infinity norm is upper bounded by 1, then a rigorous proof exists only for certain topologies. Then if for trees and complete topologies, that's a sufficient condition for the existence of synchronous solutions. 2 norm, infinity norm, different arguments. I'm going to refer to this right-hand side as the threshold. So if you're below the threshold, you succeed. And intuition is right, because the more power I inject, the more likely, finally, I will surely violate the threshold. For low power injections, the pairwise angular differences are going to be very small, and then we are in the linear regime, everything works. So this is results that some of these were derived by others, but for example, this result was in an older paper in PNAS with Professor Kuramoto. So now the question is still, what is the right quantity to look at? And can I look at it over what norms, and what is the right threshold? And so now I can tell you the new results in the 2019 paper and the transaction that is mentioned earlier in the outline slide is as follows. It turns out that with the new, more general analysis method, we've been able to show that the best tests are always just looking at this pairwise displacement, the solution to the linear problem. And this works for any P norm. Here I'm showing it for the 2 norm and for the infinity norm, but it would work for any norm. And then depending upon which norm, I get different thresholds. The threshold 1 equal to 1 is still correct for the 2 norm. The threshold for the infinity norm, we have a different threshold. I don't want to spend too much time elaborating on it. Let me make it clear that one important difference between the old result and the new result here is that this new result holds for all graphs and not just for specific topology. And so, strictly speaking, this is the first time an infinity norm test is available. And there are good reasons why infinity norm test is useful. So now, let me just quickly tell you what this threshold is. I don't want to spend much time. You just compute it out. G is just a function. Here I'm plotting it. And the P, there's beautiful geometry here that I don't have time to review. The matrix P is an oblique projection matrix that has to do with the so-called cut space and the so-called cycle space of the graph. So these are concepts that in algebraic graph theory are well understood. Suffices to say that The matrix P has several properties, and we do use them in the analysis. And here I will be silent about the details of this analysis that leads to the proof of the results. Because of time constraints, instead of showing to you the proof, let me show you. Let me continue to elaborate on this test and their meaning. So, as I said, this will be the solution to the linear problem. And I am you know, being able to use the infinity norm, which is to say the largest displacement has to be upper bounded by this quantity. And actually, as I said, really, truly, we do have a test that works for any P norm, in any P norm, and the threshold on the right-hand side is complex. It's more complex to compute in general, because it is the solution to a certain non-convex optimization problem. So while here I have explicitly obtained the two thresholds, there is also some ongoing work trying to design a appropriate solver for a certain non-convex optimization problem. And if I could do that, my test would be even less conservative. Why do I say they are conservative? Well, once again, these are sufficient conditions, not necessarily insufficient. There is certainly a gap between when this condition is satisfied. Let me take my best condition, which is this one. I have this condition. If it is satisfied, a synchronous solution exists, power can flow. If it is not satisfied, then there is a gap, you know, as you keep increasing power injection, in the end, after a while, it will not be feasible anymore, the power transmission, but there is a gap. So let's try to quantify that gap numerically. So how do I do this calculation? So I can certainly check if this test is satisfied. This requires essentially zero computation, because I just have to do some matrix product, compute a norm, apply a function. And so this requires no iteration of any kind. It's incredibly fast, and it also tells you something about the set of feasible power injection. By the way, this is describing a polytope, and so one can imagine running optimizations over this polytope. Now, on the other hand, I wish to compare that with what the solution to a nonlinear solver would be. You know, I can certainly take the Kuramoto equilibrium equation and run it to a nonlinear solver. For example, I could use fmincon from MATLAB, right, to see if it finds a solution to this nonlinear zero problem, right? Now, in order to do a comparison, I'm going to adopt some IEEE test cases that I am highlighting here. These number describes the number of nodes in the graph that they represent, so all the way up to 2,300 nodes, but starting from a very small graph. And what do I show? Here, what I show is the ratio, pardon me, is the ratio of the test prediction versus the numerical computation. So, as I said, as I increase the power injection, at some point in time, numerically determined, I won't have solutions anymore. And up until some value, I can do that with my test. What is the percentage of the true power transmission capacity? What is the percentage that my test predicts? The larger that is, the more accurate I am. If I predict more than 100%, then my theoretical test is wrong, right? Hopefully all of my percentages are less than 100%, which they are, by the way. So the best previously known test was the so-called old two-norm test, which, by the way, was only guaranteed to work for unweighted graphs. And here instead, I'm using admittances from the IEEE test cases. And as you see here, as the dimension of the graph increases, the accuracy of the prediction drops precipitously. And for example, at 2,400 nodes, the old test was capable of predicting only 0.1% of the true transmission capacity. In other words, we are 3 orders of magnitude away from the true estimates. Now, if I use my new infinity norm test, the one I mentioned is the best so far, right? The new infinity norm. Then here you see 73%, and it does drop, of course, as the network becomes larger. But still, I am at 30%, approximately 30% at 2,400 nodes. So I would say we are still failing to predict the correct value, but we are beginning to be in the ballpark, certainly much, much larger. So the improvement here is over 2 orders of magnitude. Finally, if I instead were to, you know, much of the conservativeness of my approach is the threshold. I end up estimating the threshold in a very conservative way. So if I were to close my eyes and not need to rely upon proofs and just say, what does work in practice? Well, it turns out that actually using my test, but instead of computing the threshold correctly, as I had said, one just simply plug in the number 1. Well, then it turns out that the approximate test is very accurate. It's very accurate and it seems to retain its accuracy even as the dimension increases. Equally well, or even perhaps better, I could do, and I would have also some kind of guarantees, if I could solve this non-convex optimization. Here, this non-convex optimization is solvable only for small dimensions. So in other words, these missing entries correspond to the fact that I don't have the test. And here, as you see, I am still within striking range of the actual test. All right, so let me summarize and conclude here. I am interested in this balance equation. It's a classic nonlinear static problem over a network. And I was able to answer the first 3 questions having to do with stability, capacity, and robustness to varying degrees of accuracy in a way that is essentially closed form without having to run any iterative algorithm. That's the existence question. This was the existence question, and the depth, the distance from loss of existence. Let me now talk just briefly, I have a few more minutes, about multi-stability. So it turns out that the solutions are not unique. Practical observations are that oftentimes power flows develop around loops in the graph. This is a diagram illustrating Lake Erie in the northeastern United States, where undesirable power flows arise. This is taken from a technical report found online. This is another technical report found online, and describes how even in the continental US power system, undesirable loops and sizable differences between predicted and actual power flows often arise. So overall, I would argue it's of interest to understanding what are all solutions to the power flow equations, right? And so, we just discussed uniqueness. Are the solutions, they're not unique? How many are them? Can I localize them? Can I understand this relation between loop flows that is interesting in practice? And so a very simple example shows very quickly that it's very easy to see why multiple solutions exist. Imagine I have a complete graph with 3 nodes. Sometimes people refer to the complete graph with 3 nodes or a triangle, right? So now, on a complete graph with 3 nodes, if I select all nodes and I put them at exactly the same location, and I assume that my weights are all equal to each other, and I assume there's no power injection, then of course this is the solution here on the left. On the other hand, this is called the phase synchronous solution. Now I have full phase synchrony. All of the phases are identical. On the other hand, I could be in a situation where, no, I actually place the angles equispaced along the circle. This is called the splay state. And it turns out that even that you can check into substituting into the equations is a solution. So it's not unique. How do we elaborate on this? Imagine, imagine I label, blue, green, and red the 3 nodes. And imagine I perform this mental calculation. I compute counterclockwise differences from blue to red, from blue to green, from green to red. And then counterclockwise, I get a negative angle that comes all the way back to the blue node. So when I sum counterclockwise angular differences on the left image in the slide, I obtain 0. Instead, if I just take the red node and shift it a little bit, and it comes here, counterclockwise, counterclockwise, the shorter counterclockwise arc is this way. Now, if I sum the counterclockwise differences, I obtain 2 pi in the example on the right. This is assuming I measure counterclockwise. I could measure clockwise, or in any case, I could change the ordering or the labeling of the nodes. Possibly, I would get minus 2 pi, depending upon how I set up the convention. The bottom line is that if I normalized by 1 over 2 pi, the sum of the counterclockwise differences in this 3-dimensional example is a multiple of 2 pi. Well, and then I scale it, and so it's a natural number. 0 plus 1 minus 1, an integer number. I'm going to refer to that as the winding number of this cycle, the winding number. Now, this is, in other words, I have a graph, I have a cycle, Along the cycle, I sum counterclockwise differences and I obtain the winding number, So now, if I have a graph that has multiple cycles, right? What I would like to do is I will focus on something called an independent basis of cycles. This is an algebraic graph theory. So, but I don't want to use redundant all of the cycles. If you have two small cycles, they're connected, there's one bigger cycle. So I'm just going to focus on an independent basis of cycles. And then I compute the winding number for each of them, each of the independent basis of cycle, each of the dependent element of the basis, and I will call that the winding vector. As I change the angle theta, I get a different winding vector, right? Let me make one more comment. When I shift the angles a little bit, suppose I change the green location a little bit, the winding number does not change. So the function that maps the set of angles to the winding vector is a function that is piecewise constant. And what that means is that, right, here I'm saying that the winding vector, well, for a single cycle, the winding number takes only a finite number of possible values. It's piecewise constant. And it takes value in a finite set. Now, what that means, if you think about it for a few seconds, is that tells you that you can take the entire torus. Let me go to the pictures. You can take the entire torus and you can split it into cells. This is the cell where the winding number is -1. This is the cell where the winding number is 0. And this is the cell where the winding number is +1. Because the winding number takes only a finite number of values, right? So this is a 3 torus. This is P3. It means 3 angles. So I am capable to draw a 3-dimensional example. I cannot visualize larger dimensional systems, but the same picture is there. So this is called the winding partition. The winding partition. And in other words, the entire torus is equal to the union of these cells. And the cells themselves are those defined by the idea that the winding vector has to be constant. Now, why is this relevant? Well, but before I continue, just a little detail. Each cell is connected. Each cell is invariant under rotation, which is a natural property to ask for. And each cell, there is a natural way of mapping that. And each cell is like a convex polytope. So this is also a useful property for optimization purposes. Let me not spend too much detail about the setup of this winding partition. I will just say, why are we interested in it? This is my last result. Once again, we are interested in finding synchronous solutions to the Kuramoto equations, which correspond to active power flows, which are equilibrium solutions of this equation. We know we give a sufficient condition for one solution to exist, but we know that in general, more than one exists. What is it that we know now? What have we discovered with this construction? Why is this construction useful? This is the theorem. I now can tell you that each winding cell has at most one equilibrium point of the kind that I'm interested in. At most one equilibrium. So if you go back to this picture, at most one equilibrium is here, at most one is there, at most one is on the right. So this tells you that if you have the torus and the graph over the torus, you do the partition, you can count how many cells there are, and that is an upper bound on the number of solutions, because in each cell there's at most one. Moreover, this winding number for a cycle, or let's call the cycle loop for a second. Each loop has a winding number. The larger is that loop, the larger is the power flow that flows around the loop. So that the physics of the problem is nicely captured by this mathematical concept. And finally, even though I am not writing the formulas here in the interest of brevity, that's all the tests, the sufficient condition, right? The pairwise displacements, infinity norm, less than the threshold, that test can be easily modified to become a test for existence and uniqueness in each individual cell. So on each cell, I have a test for existence. And if that test is satisfied, it must be unique because of this theorem, right? So I now have an algorithm to compute every solution to this active power flow equation by first computing the winding cells and then checking one by one in very simple closed form. Now, I have another 30 seconds and let me summarize. I have talked to you briefly about linear network systems. I'd love to talk more about it if time allows in live form. And then I've talked to you about tests for synchronization and an understanding and test for multi-stability, existence of multiple solutions. There is an emerging theory, these are 4 minutes. There's an emerging theory that I would like to talk to you in the future about that allows me to take these ideas that I have applied only to Kuramoto and tries to extend them to a broader class of nonlinear network systems. Clearly of great interest at this point in time are strategies for learning and control of infrastructure networks such as power. But then I also find it extremely interesting that this area of network systems, as illustrated up here by these examples, provides us with a fantastic opportunity for collaborating and reaching out to our colleagues in sociology, in biology, in economics, physics, and so forth. So this is really an exciting area. I hope I've been able to convey a little bit of the enthusiasm and some of the recent results in this area. I do once again wish to thank everybody for your kind attention, and I do very much hope to have a chance to talk to you in a live session during the conference or even afterwards. These slides will be on my website shortly, and with this I wish to thank you all again and hope to meet you in person someday soon. Bye-bye.